All right, hey folks, I'm gonna do the. I'm basically just gonna go over the test. I'm just gonna do it right here and go over each problem as much detail as I can, and hopefully it helps you in your reflection process here. Um, all right, this first problem, obviously it's indefinite. There are no numbers on the integral, so we'll just do an antiderivative here. So let's see, this would be x to the seventh. Let's double check that. Take the derivative of x to the seventh, you get 7x to the sixth. So we're good there. All right, minus, well, my new exponent here is going to be to the 6. 6 times what? Gets me 2. So that would be 1/3. And as always, I'm just going to double check. 6 times negative 1/3 gives me negative 2 x to the fifth, so that's good. And last one, antiderivative of cosine is just sine of x. Don't forget. Yeah. All right, fundamental theory of calculus, that means we have to do antiderivative, which this process up here, and then we have to also plug in the 5 and negative 5 and subtract. So let's see, e to the 4x, if that was my antiderivative, and I derived that, that would give me 4 e to the 4x, because it's e to the 4x times the derivative of 4x, which is 4. Well, that 4 doesn't exist up here, so what I really need is a 1/4. I'll get rid of derive 1/4 e to the 4x, I just get e to the 4x, which is what I started with. That's what I want. So that's my antiderivative, e to the 4x, and we're integrating from negative 5 to 5. So that's fundamental theorem of calculus. Let's plug in the 5 first. That gives me e to the 20. Oh, wait, sorry. Wait. Let me slow down here. This is my antiderivative, right? And when I derived it, I got this. Oof, I caught that. So I'll plug in these numbers now. So 1/4 e to the 4 times 5 is 20. So that's just e to the 20th over 4. Minus, same thing, now plug in negative 5 in, so that would be 1/4 e to the negative 20, which is be minus 1/4 e to the 20. That's what the negative exponent means at the bottom. I would accept this answer, but let's just go ahead and see real quick what it would give us. So let's go to the calculator. It's a big number right there. 12129. 2129. 12129. 1298. 852. Cool. So again, I'm more worried about this process than what you actually get out of the plugging that in. Okay, so I'm going to graph these two things here. I've got these two equations. It's going to look something like a parabola and a straight line. That's what I've got here, a parabola and straight line. So that's right here. I got these graphs right here. So we're integrating from negative 2 to 5. Now this is just area, not volume. So we're just taking top minus bottom. That's it. We're just getting all the areas right in here, all those slices. So we're integrating from negative 2 to 5. 2 to 5. Top equation is the straight line. Top minus x squared minus 2x minus 4. That's the bottom. Dx. And that's it. Since I don't have to use fundamental theorem of calculus, I can just type this in, and I'm going to do that. One moment. Okay. So that would give us negative 2, 5, x plus 6 minus x squared minus 2x minus 4 dx. 57.166. Oops, sorry. Give me one moment while I figure out where the. Oh, that's right. It's good next to. Ooh, sorry about that. Okay. So 57.166. Cool. All right, let's move on. Evaluate this, it means find the derivative. This is two things multiplying, so that's product rule. Product rule. So that would give us derivative of the first is 6x to the fifth times the second by itself, plus the first one by itself times the derivative of secant of x. So I'm just going to look that up. And I found that the derivative of secant is tangent times secant. So tangent of x, secant of x. I could factor something out here, but it wouldn't really help me change anything. So I can leave it like this, but I'll also go ahead and put the factored out answer. They have an x to the fifth and a secant in common. So secant of x, x to the fifth. And then inside we still have a 6 plus x times tangent of x. Either of those are completely acceptable. Now, if there were like a fraction and we needed to, then you would need to do this process right here, but there's nothing wrong with that. Okay, now we're on to the volume problems. So I'm going to graph this. It's going to be some negative parabola in the x-axis. Okay, that's kind of nice. So let's graph that, see what it looks like. All right, so I've got it graphed here. It says regent in the first quadrant under this blue line right here, 6 minus x squared, and the x-axis. So that's down here. So this is a disk problem. And I'm just using vertical slices. These are the, I've got my shape kind of right here and rotating around this way. So it's just going to be giving me something like that. Right, so, there's one slice, it's just a disk. Let's see, disk is, well, let's look at what we're integrating from what to what. Vertical slices, so I'm going from 0 to 2.449. 0 to 2.449. And it's just radius, so that's a radius, pi r squared, and the radius is just going to be the height of that graph at any moment. So pi r squared, I got pi r squared dx, so I'll type that in here. Pi r squared dx, 147,749. Cool. And some units cubed, I'm going to write that, that's fine. Okay, so for all these questions, we use the same region, and that's this one right here. Okay, so I might be referring back to the same picture. Come on, erase for me. Okay. Find the volume of the solid rotating the region bound by these two curves around the x-axis. So first, that's this one right here, x-axis. So here, we can do vertical slices, and it would end up being a washer then. One slice would be this part, and then some other part, and that makes a washer. Sorry for my crude drawings. So I'm going to put washer, and we just need outer and inner then. So let me just get these 2 points of intersection, and that way I always have them. Just keep using them. So we're talking, what is that going to be? 1.79 to 6.7. Where was this one? 1.8. Okay, so looking at my graph here, I got my x values starting at 1. If you look at the intersection point, it's about 1.7, or you can just put 1.8. So I put 1.788 to 6.712. That's down here, the x value down here. But 6.712 into. All right, this is washer method, so I just need the outer radius minus the inner radius. So let's look at the picture here. This is your outer one, okay, because you're rotating this way. So that's the red line. So the outer is just going to be, I need pi, and then r is this, squared minus pi, the inner, which is the blue one, 1/2 x squared. And I think I've already gotten that one worked out right here. Let's see. It's this one. Pi r squared minus pi. Over here. Oops. So pi r squared minus pi. 537 about. I'll put about. Put the little about symbol here. The squiggle. 537.705. 730. Cool. Okay, let's look at the next one. Same region, but now the y-axis. Let me erase all this. Around the y-axis, this way. Okay, so this is where if we were to do washer method, it would get awkward right here because it's the same graph. So you could either chunk this up in a couple of integrals, or we could just use shell. So here'd be like my one slice that's been rotated around. So let's just do shell now then. Shell. Let's see. Shell is, so actually, so I'm still using vertical, and so I'm going to have the same integration points as my last one. That's convenient. 6.712. But I need 2 pi r times the height. So let's see what that's going to be times dx. 2 pi r. Since it's just going to the y-axis at any given slice right here, your r value is just the same as x. So that worked out well. Height, that's just going to be the top one minus the bottom one. See, at each slice, it's just the red one minus the blue one. So let's just use that. Red one minus blue one. Negative x squared plus 8x minus 8 minus the blue one. Negative 1/2 x plus 4 and times dx. That's it. That's it. Let's see what we get when we do that. So I got, yeah, let's make sure I type that in right. 531.447. 531.447. Cool. Let's keep going. The volume. Okay, so x equals 10. Let's look back at it. X equals 10. That's right here. So rotating around this way. Again, washer would be awkward right here, so we're just going to do shell again. Let me erase this. Okay. Let's see. So shell. Still doing vertical slices here. This is still a vertical slice of a shell. Right, you get some shell kind of looks like that. So still vertical slices. So still same integration. 1.788 to 6.7. Let's see. 2 pi r. Okay, but this is where it's going to be tricky. Let's look at the picture. R is this distance right here. Okay, like if there's your slice, here's your r. Here's your r. Here's another r right there. I'm just going to draw a couple to help show what I'm doing each time. Well, it's always starting at 10. And each time I am subtracting, well, the x value, right? Some x value. It's just 10 minus the x value. Because right here is like your x value. And you want the whole thing, all of 10, take away that little bit right here, and leaves you with 10 minus x. So for each step, it's just 10 minus x. That's your radius. Put that 10 minus x. Conveniently enough, the height is going to be the same as that last one. It's still shell method from that last one. The height's still just the top one minus the bottom one, red minus blue. So if I were really good with OneNote, I would copy and paste that part up there, but I'm not going to do that right now. So I'm just going to rewrite it. Oh gosh, go away. I don't want you. Okay, go away. All right. So I'm same thing again. Negative x squared plus 8x minus 8 minus 1/2 x plus 4 dx. And that's it. That gets me about, I've already typed in over here. Is this one here? Yeah. 719.58. And for those of you wondering why that's so much bigger than the last answer we got up here, well, considering that up here you were just rotating it around something it was relatively close to, an axis. See, now it's over here at the 10. This is the rotation. So with a much bigger rotation, you're going to have a much bigger object, so the volume is larger. And last one, rotating around the line y equals 10. So I can't draw that one as well because it's above this little graph here. But it's going to be up here somewhere. We're rotating this way. Rotating this way. So this is a washer. Here's my slice. I'm going to draw that full slice. I've got some washer. Okay. Nice. So I've just got an outer and an inner here. It'd be a little bit more difficult because you have to think about, well, this is y equals 10. Let me get it set up here. This is washer. Still vertical slices. Still vertical slices. So same integration. 788, 6.712. And washer is pi r squared minus pi r squared with the outer minus the inner. Let's look at the outer. Well, the outer is from 10, and then you're going to take away this blue one. Each time it's the full 10, take away this blue distance right here. So 10 minus the blue one, because it's the y value of that blue one. And that gives you this distance that you want. That's the outer. So 10 minus the blue one. Pi 10 minus negative 1/2 x plus 10 minus the blue one squared minus pi. Now the inner one, I think is the same thing. It's going to be 10. Oops, so much going up here. It's going to be that full 10. Take away this y value, or that, and then you're left with this distance, and that's the inner radius. 10 minus x squared plus 8x minus 8 dx. Squared, pi r squared dx. There's our integral. I've already typed that in. Hopefully I did it the same way. Let's just check real quick, make sure I did actually. 10 minus the outer one squared, 10 minus the inner one squared. Make sure you don't forget squares. 712,805. Great. All right, so that's all the heavy stuff. Let's look at the last two problems here. Language. I'll just talk through them. Language, what helps you determine what a vertical slice or horizontal slice? So it depends on the method you're going to use, right? Washer, shell, that kind of helps determine it. Shell, washer, that kind of helps determine it. And then method, and then I guess rotation, really. Like those two things is how we determined it. Like the rotation of the method, then we determine vertical, horizontal slices. Same thing here. Going to use shell or washer. Well, if you are, I'm just going to say this one. I'm going to write out. If you're subtracting the inner and outer, but it's the same graph, then you can't do washer. You can't differentiate between the two. So, just only say like looking at the graph and deciding if washer would work, if it's just one curve that you're subtracting from itself. It's kind of difficult. All right, so I hope this was extremely helpful, and you can let me know what questions you have beyond this.